So we left off with right triangle trigonometry, and mathematicians were kind of greedy. They wanted, if I write sine of alpha or sine of x, that only makes sense if x is an angle that can live in a triangle that already has a right angle in it, right?
Right.
And that bothered mathematicians. They just wanted to extend the meaning. I mean, it's called the domain. The domain of an expression is the set of numbers upon which the expression can be meaningfully interpreted. That's called domain. And so they wanted to extend the domain. The ultimate goal was all angles. Actually, they went with all real numbers because if you recall, radians they're real numbers. They're just a length over length. And so the goal was to go all the way until you can have positive, negative, thousands and thousands, every number. They wanted a sign for every number. So here is the first thing that we can do. So if this is alpha here, then sine alpha was A over C. Cosine alpha was B over C. And tangent alpha was A over B. And the other three, they're reciprocals. We could model the whole thing with the 3, 4, 5, which is like kind of the cutest little. So let me call this beta. Sine beta is 3 over 5. Cosine beta is 4 over 5. And so the idea was that if we happen to scale it down and replace this with a similar triangle where the hypotenuse is 1, 1 is a very easy number to divide by. So in this case, we would divide every side by 5. And we would get 3 over 5, 4 over 5, and 1. And if you look at sine beta, it's 3 over 5 over 1, or just 3 over 5. So if you have a fraction and you make the denominator 1, then that ratio can just become a length. That's how radian was kind of done, right?
Yeah. Oh,
and so
that's nice.
Yeah, it is nice. And there is a proof. There is a problem, like prove that if x is something like this, then sine of x plus cosine of x is always greater than 1. Well, if we scale down this triangle by dividing all sides by c, what we're gonna get is sine alpha is this side, cosine alpha is that side. And then you just apply the triangle inequality. Right? Sine alpha plus cosine alpha is bigger than 1. So that's the beginning. And before we start, I just want to mention one thing. When we took this, the half of the regular, the semi-regular triangle, the 30, 60, 90. Remember, this was 2, this was 1, and then this turned out to be square root of 3. 2, 1, half, just you can visualize the other half there. So we're going to scale this down. So instead of 2, this is going to be 1. And instead of 1, this is going to be half. And instead of square root of 3, this is going to be square root of 3 over 2. Now, as a teacher, half as a decimal is 0.5. But square root of 3 over 2, if I punch this in, square root of 3 divided by 2, as an exam, that's almost an A, 0.866.
Yeah.
So what I'm telling you is that it's visible. So all you got to remember about this triangle is that the obviously shorter side is half. The obviously longer side is that root 3 over 2. And they are obviously opposite the 30 and opposite of the 60 accordingly, correspondingly, whatever. So that was the first. That was the first step was scale them down to hypotenuse 1. And then what we're going to do, the second part of the trigonometry is called unit circle trigonometry. And whenever we are enlarging our world in mathematics, we want to preserve the math we already have. So this definition should not conflict with the previous definition. So that means that unit circle trigonometry defines sine, cosine, tangent for every angle. But if the angle happens to be between 0 and 90, it has to say the same thing as the right triangle trigonometry, right? So where there is an overlap, they have to agree. Otherwise, they would say, no, we're not doing that. And so here is the definition. So the unit circle has radius 1 and it's centered at the origin, 0, 0. Now, you know, circles have equations too, because this one has the following equation. You can look at this as x and y for this point P, x, y, and then x squared plus y squared equals 1 is actually the unit circle's equation. So every point will do that, right? It's the Pythagorean theorem on this triangle. Mm-hmm. Except it even works here where it's 1, 0, and there is no triangle, but it works. 1 squared plus 0 squared equals 2. So there are 4 points where there is no triangle, but the equation works.
That's fun.
Yeah, that is fun. And so they said, here, we're going to define. Now, let's grab your angle. And, you know, one of the things that I think was really needed is imagine a particle going around for a long time or very fast. Then it wraps around a lot of cycles. So if we measure that in degrees, we wanted to be able to put sine and cosine to thousands of degrees because we wanted to trace this. So we're going to basically start thinking of angles as rotational angles, where this is 0 degrees, and this is the positive direction. So here is about 30, 60, 90, 120, 150, 180. I don't know, this is 180 plus 45, that's 225. And this is 180 plus 90, that's 270, but it is also negative 90. Right?
Right.
And so there is this concept of coterminal angles. And coterminal angles are basically, you took a walk, I took a walk, and we landed on the same path, but I might have gotten an extra lap. But coterminal angles, they terminate at the same point. And so the picture will be this. So for example, 10 degrees and 370 degrees are coterminal.
Oh, I see. Yeah. That is fun.
Yeah, every time we agree, nothing is for free. So now there is a little bit of confusion because lots of angles will have the same sign. Coterminal angles are indistinguishable. All of their trigonometric functions will be the same. So if you ask sine, cosine, tangent, blah, 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 you will not be able to tell these two apart. Because the definition is first, let's define a rotational angle and, you know, play it out and land somewhere. So if you land at 40 degrees, that's the same as 40 plus 360 or 40 minus 360. And then also, if we solve trigonometric equations, we always like all the solutions. So now how do we write down this freaky? So we basically say for all angles, coterminal to 40 is 40 itself plus an integer number times 360. We usually use k, where k is an integer. But it's kind of weird. If we look at this expression, here is k, here is 40 plus k times 360. So if k is 0, we put 0 into this expression, we get 40, right?
Right.
We put 0 into k, but we can also put 1 into k, and then we get 400. Or 2, where we're going to get 720 plus 40, 760. And we can also put negative 1 in there. Then we're going to get negative 320. These all look the same. If you draw it on the unit circle, they all land on the same point. They're coterminal. And this k is kind of strange because it's not like x that casually takes a value that we're looking for. If we want to express all of them, that means that we have to force k to take every integer value. It has to take the value 0, it has to take the value of 1, it has to take the value of 2, negative 1, negative 2. So it's kind of it's not just some integer with a casual value, it's actually all of them to pick up all of the angles. And it's a kind of a one-to-one correspondence. So for every value of k, there is a coterminal angle. That was the payment for rotational angles, right?
Yeah.
And so there are six identities that I can tell you that sine of alpha is going to be the same as sine of alpha plus k times 360, where this is annoying. We have to say k is an integer, k is an integer. There is a shorthand for this. This is a capital Z. This is the symbol for the set of all integers. This is element of. This is just, these two statements are the same. K belongs to the set of all integers. That means k is an integer. But even that's sloppy because it's all of them, you know, it's that infinite form. But I guess here we can say for all k integer. And usually you're going to see more intimidatingly sine of x equals sine of x plus 2k pi. Now, x kind of indicates degree is not allowed. Alpha is kind of English, like an angle.
Yeah.
That is, it's soft rule. It's not even a rule. It's just kind of a lazy convention that if they say alpha beta, you are allowed to think and say degrees. But if you say sine of x, that's a real number. It has to be in radians.
That's why there's the 2 pi, right? Because of instead of 3.
That's the 360. And yeah, it should be k times 2 pi. But we mathematicians, we are a little bit anal. And we like first the numbers, then the letters, right?
Right.
It should be. Yeah, so this is going to be the 2k pi. And it's just all over the place. And there is 5 more. We can state the same thing about cosine and tangent and cosecant and secant and cotangent.
Right.
Everything is the same. If the angles are coterminal, everything is going to be the same. And I think a particle moving along a circle was I think that was a motivating factor there. Although I'm just making up this stuff. So draw alpha as a rotational angle. Now, no matter where it stops, it's gonna hit the, you know, it always reminds me of action movies when the radar, that thing goes around, right? I'm gonna go a little bit more than 30 degrees, but it could be a little bit more than 390 degrees or negative, you know, you can always add or subtract 390, but that's our angle alpha. And then no matter what the angle is, the unit circle and this ray representing the angle will have an intersection point P. And we define cosine alpha to be the first coordinate of that point and sine alpha to be the second coordinate of that point. You know, I alphabetized it. So first X, then Y in the alphabet, first cosine, then sine in the alphabet.
Oh, that's such a nice way to remember.
Yeah. I guess, yeah. So the first thing we should check for, well, does this hurt the old definition? So it's a little bit too big, but let's imagine this is 30 degrees. Well, if this is 30 degrees and the hypotenuse is 1, we have this 1/2 square root of 3/2 triangle.
Yeah.
It's a little bit too big. And so what are the two coordinates of this point? The two coordinates are, well, we start from the 0 and we go root 3/2 to the right. So the x coordinate of this point is square root of 3/2. And the y coordinate of this point is 1/2. And if we apply right triangle trigonometry, we better get the same things, right? The first coordinate is the cosine, the second coordinate is the sine. So if we apply right triangle trigonometry, then this side over 1 is sine 30. That should be half. It is half. You see half.
Yeah.
So it works. It fits. So this is called the first quadrant. In the first quadrant, you can define angles as rotational angles and use unit circle trigonometry or right triangle trigonometry, and they will give you the same thing. But then, well, we can hit 90 degrees. 90 degree cannot sit in a triangle that already has a 90 degree, but there are two coordinates of this point, right? The first coordinate is 0, the second coordinate is 1. So cosine of 90 degrees is 0, and sine of 90 degrees is 1. It no longer conflicts with the right triangle trigonometry, and we can always ask the calculator, sine of 90, that is the one. Oh, and because of our definition, this is always going to be true, that sine squared alpha plus cosine squared alpha is always going to be 1. That's the Pythagorean identity that will remain true. That's the equation of that circle. All right, so I always feel so bad for people who, now this is my rant, so I'm going to give you one of the, there are so many things that bother me about American education. One of the things is that it's like I see calculus students doing this. Like, come on, you don't need the visual there. You know this. Let's add the same thing to both sides. Big boys do. Here we promise to do something, and then we figure out what that is, and we do not need visual clues like that. There is that hanging on to visual clues when it's just trivial. That bothers me, especially because where it matters, where there are visual clues, then people start memorizing crap because they don't know how to look at a picture. That drives me nuts. So what's going to happen is no memorizing. No memorizing. And the other thing is that we never let right triangle trigonometry go. For instance, let's look at 120 degrees. So 120 degrees is 90 plus 30. So this point here represents 120 degrees, but this here is a 30, 90, 60 triangle. Why? Because 120 is 90 plus 30.
Yeah.
Now, because we know this triangle, we know that the hypotenuse is 1, the obviously visibly shorter side is half, the visibly longer side is square root of 3/2. That's right triangle trigonometry. But now we're going to use these lengths and the orientation of this triangle to read the coordinates of this point. Like, which way is it stuffed into the, like, the x coordinate here is -½
Right.
And so people are memorizing, they're using little memo technique to memorize what is right there. So cosine of 120 is -1/2. And you can tell, even a sloppy little picture, you will be able to tell which is half and which is √3/2. It's very visible. On the margin, you're going to draw a little bit. That's 30, that's 60. It's still visible. Which one is? And then sine of 120 is plus square root of 3/2. And so people have this, there is this little poem that, or some memo technique where they memorize what is positive, what is negative. I'm like, look at it, right?
Yeah.
It's just a mud wrestling every time I teach that. Here is cosine of 120 is -½
Yeah. Wow. Oh, I love
like-
this. I've seen like the full unit circle before, all filled out, and without knowing, oh, okay, that right angle trigonometry. It's like, why try to memorize instead of understanding why it works?
Exactly.
Wow.
If you visualize, and you're a visual type, I'm pretty sure otherwise you wouldn't be studying what you're studying. So there are 4 groups of famous angles. If the angle is not famous, then calculator automatically. And now these values are always going to be between -1 and +1 because the x coordinates and the y coordinates of, so you're not going to get beyond 1 or beyond -1. It's always going to be in between. But there are 4 groups. Here is group 1, 30, 60. And you can tell that sine of 30, oh, I never know what to start with. So if we go x coordinate, y coordinate, here the x coordinate is long, the y coordinate is short, right? And with 60, it's kind of the other way around. But there is 120, 150, 210, or -150. Sometimes one is better than the other, right? Okay, now we're gonna play a little game. You tell me, what is the x and the y coordinate of this point, where 210 is 180 plus 30?
Okay.
You tell me.
Okay, so the x coordinate, because it's this way. Okay, the x coordinate's the long side. So on the long side, that's where it's √3/2. And then the y coordinate on the short side, that's 1/2.
Okay.
But I got to think about the negatives. The negatives.
Mhm.
Wait, it'll be -√3/2 and -1/2.
That girl, you got the unit circle. Thank you. Right.
Cool.
Yeah. And so the first coordinate is cosine 210 is -√3/2. And this is a number you're going to recognize after a while. It's 0.866. So if I punch in cosine of 210, oh, it's -0.866. That's that √3/2. And then the sine of 210 is -1/2. And 240 or 240 or -120. -60 or 300. Of course, there are infinitely many other labels, but these are the 2 most useful ones. And -30 or 330. And these are automatically, the sine and the cosine are all plus minus either half or √3/2. It's just how is that one triangle stuffed into the unit circle? That is the question. So that's one group. And whenever it's kind of, it's weird. If it's 28, you use the calculator. If it's 30, exact values, because we know. That's why I said that there are 2 trigonometries. Well, really 4. Right triangle, unit circle, famous angles, not famous angles. Here is the other group. They're related to the 45. The good news is, because of the symmetry, well, let's see what triangle. With 45, we start with 1, 1, root 2. And then we scale it down to hypotenuse 1 by dividing by root 2. So we get 1 over root 2, 1 over root 2, 1. And and so in case of 45 or 45 related, it's 45, and then we can think of this as 90 plus 45 or 180 minus 45, 135. And then 180 plus 45 is 225. And then this is either negative 45 or 315. And so the x and the y coordinates are the same. It's the same 1 over root 2, which is 0.707. If I say sine of 135, well, 135 is this. Oh, this is called the first quadrant, second, third, fourth. I don't care about the labels, but I see that the x coordinate is negative, the y coordinate is positive. So if I punch in sine, that's still going to be positive. That's at 0.707. That is 1 over root 2. If I were to square this, I should get half. So, yeah, and then the third group is these guys, the ones without a triangle. 0, 90, 180 and minus 180 are the same point because they differ by 360. Kind of cute.
Right.
270 or negative 90 and 0 or 360 or minus 360, they're all here. And so the sine and the cosine, it's all going to be 1 or 0 or minus 1, depending on whether, well, you could just read the coordinates. So
Right.
And yep, even so, if I worry about 30, oh, which is the root 3 over 2, or what is sine of 30? I don't have to draw it, but this is what I visualize. Short, long. Even a tiny sloppy picture will tell you.